So welcome back to the next part of lecture 17, part 3 for today. So you can see me again. And I would just introduce this notion of taking a linear map and associating to it an operator. And so what I thought is I would actually spend some time looking in more detail at this particular linear operator, which is actually the one that showed up at the beginning of our first example for today. Okay, so I'll make myself disappear so we have some more room. So here's the operator that we're working with. It's the same one that I had at the first part of today's lecture. And let's say I want to know is, well, what is the operator t squared, right? So just by definition, that just means this is the operator that you get when you take an x, y, z, you plug it into t, and then you plug that input back into t, right? So this is the same thing as saying t evaluated now at 3x plus 2y plus 4z, 4y plus 2z, and 8z. And now things get a little kind of messy because we got a very big expression here. So we're taking this term and plugging it back into t. So I will get, as my final output, I will get 3 times the first coordinate. So the first coordinate is 3x plus 2y plus 4z plus 2 times the second coordinate, so 2 times 4y plus 2z plus 4 times the last coordinate, 8z. So that's the new first coordinate. Now I take 4 times the second coordinate, which was 4y plus 2z, plus 2 times the last coordinate. And then I take 8 times the last coordinate, so 8 times 8z. Okay, so now we want to clean this all up, and so I've done the arithmetic beforehand, but so you kind of expand this all out and you collect all the x's together, you collect all the y's together and all the z together. So we end up with 9x plus 14y plus 48z as my first coordinate. Then we have 16y plus 24z as my second coordinate, and my third coordinate is 64z. Okay, so this is what t squared is. And now if we wanted to figure out what t cubed is, we would take this output and stick it back into t, and then we could find t cubed. And then we can continue this process. Okay, so now let's go back again to this particular polynomial. Say we were looking at the polynomial 2 plus 5z. Then when we stick this operator into this function, we get, by definition, we get 2 times the identity operator plus 5 times t squared. Okay, and so you want to think about this, right? What this means is this is an operator that tells me where I can send a triple. Okay, so where does it send the triple x, y, z? Well, it will send it to 2 times where the identity operator will send x, y, and z, plus 5 times t squared, wherever x, y, and z get sent to by t squared. And this part is easy. The identity operator sends x, y, z to itself, so I get 2 times x, y times z. And here I get 5 times everything that I have up here, right? So 5 times 9x plus 14y plus 48z, 16y plus 24z, and 64z. And we're almost there. You kind of have to then expand this out and then collect everything together, right? So PT is the operator that takes the pair x, y, and z and sends it to 47x plus 14y plus 48z. That's where the first coordinate is. The new second coordinate is 18y plus 24z plus 66z. 18y plus 24z is the second coordinate, and 66 times z is the third coordinate. Okay, so we take our original t, when we can make a new operator from that t by somehow combining and using composition, and that we get a new linear operator right here. I also want to show you that you can actually get this information via the matrices, okay? So we already saw what the associated matrix is, right? It's this matrix, and if you take the square of the matrix, this is the square of the matrix that you end up getting by using matrix multiplication. So what I have here, right, is the matrix version of this linear operator, because this I would correspond to the identity matrix of size 3, and this matrix right here, mt squared, would correspond to the linear operator t squared. Now I'm skipping some details here because we haven't actually proved all of these facts. They will come up, but I just wanted to show you that you could look at everything at a matrix level, right? Because what is this equal to? I get 2 times the identity matrix plus 5 times the matrix I get from the square, right? So I get 9, 14, 48, 0, 16, 24, 0, 0, 64. And if I look at the resulting matrix, I get 47, 14, 48, 0, 18, 24, 0, 0, and 66. And if you look at all these numbers here, these are the exact same numbers that show up in here, right? So what's happening here is that you have that MPT, right? So this is the matrix of the linear operator MPT is found by applying the polynomial to the matrix MT. So what you can think of is we've taken the matrix MT and we've plugged it into our polynomial. So this would be kind of like a polynomial version of a polynomial version of applying an operator to a polynomial. Okay, so I hope this example helps kind of with some of the details. And a couple last facts here that are kind of useful about this is once you fix a linear operator, you can define a function from the set of all polynomials to the set of linear operators by taking the polynomial p and take the corresponding linear operator, right? So that's what we were doing here. We were thinking of taking this polynomial and mapping it to this linear operator. And it turns out that this map is actually a linear map, okay? So remember what that means. This means that p plus q evaluated at t. So first taking the polynomials and adding them and then turning it into an operator is the same thing as taking the operator coming from p and adding it from the operator coming from q. Right? So we get this fact, get the linearity, and then we get the scalar property that we could take the scalar of my polynomial and turn it into an operator. And that's the same thing as scaling the operator that I get by plugging in p into my function. Okay, and so if you hear some stuff in the background, my daughter's doing her French class, so hopefully it's not disrupting the sound here. So I apologize for that if it is. And finally, the multiplication property. We also get a multiplication property is we fix any t, then for all polynomials p and q in our set of polynomials, we have the fact that you could first multiply the polynomial. Okay, so this is the polynomial obtained by multiplying p and q, turning into an operator. And on this side, what we have is the composition of the operators from P and Q. So what we have is like, it doesn't matter which order you do it. You can first multiply the polynomials together and turn them into operators, or you can first turn the polynomial, take the polynomials, turn them into operators, and then compose them together. Okay, so we'll pause here, and then in that last part, we're going to talk about the existence of eigenvalues, and using this notion of polynomials is going to be very important to prove that.